Okay, here's a very simple rational function. Can you tell me what the zeros of this function might be? Does it have any zeros?
2 and -3.
Okay, actually 2 is not a zero. 2 is a zero of the denominator, and that's important. Okay, but it's not a zero of the function. -3 is a zero of the function though, because if you plug in -3, you're going to get 0, right? So I should say x equals -3 is a 0. So if we're trying to graph this thing, we know that at x equals -3, the graph has to pass through this point. Or at least it has to touch the x-axis at this point. Okay? Also, we can evaluate the function at x equals 0 r of 0 is 0 plus 3 over 0 minus 2, which is -3/2. So if we got -1 here, -2 here, the graph has to go through this point. Okay? Okay, now we have this 0 of the denominator. Well, r of x is undefined when x equals 2 because division by 0 is undefined. So and I messed that up in the way people often mess that up. Okay, r of 2 is undefined. R of -2 is a perfectly good number. Okay? Can't blame students for doing it when I keep doing it, but I know the difference. Okay. And so do most students. Okay, so, and they're probably better at fixing themselves than I am. Okay, x equals 2. Denominator 0 at x equals 2, right? So the function is undefined. So at x equals 2, there is no point on the graph above or below x equals 2. Okay? No point on the graph at which x equals 2. Now, one thing we want to do is we want to kind of look at the x-axis to see where the function is positive and where it's negative. Okay, so I'm going to draw the x-axis again here. Lower. So, nothing really all that new that we haven't talked about. We'll put it in terms of very simple function, x plus 3 over x minus 2. Okay? And we immediately saw that numerator is 0 when x is -3, denominator is 0 when x equals 2. We know that when the denominator is 0, the function is undefined, so we say r of plus 2 is undefined. Okay? We know that when the numerator is 0, the function is 0, unless the denominator also happens to be 0. We're not worried about that just yet. Okay? So when x equals -3, you're going to have a 0. So we can put that information on a graph. We know we have to go through the point -3. We know there can't be a graph point when x equals 2 because your division would be undefined. We also plug in 0 to get the y-intercept. R of 0 is -3/2, so there is our y-intercept. So the graph has to go through this point and this point. It can't touch this line. It turned out it has an asymptote at this line. Okay? So now we're just looking at what the signs of this thing are on the intervals into which the x-axis is partitioned by points -3 and 2. Okay? So to the right of x equals 2, well, x is bigger than 2 at all those points. It's not a surprise. Okay? So if x is bigger than 2, x plus 3 has to be positive, right? And x minus 2 has to be positive, right? So I'll kind of color code this because everybody loves pretty colors. That's the interval from 2 to infinity. We don't include 2, so I'll put a big old closed dot there. Okay? There's our interval from 2 to infinity, and x plus 3 is greater than 0 since x is greater than 2, right? And x minus 2 is greater than 0 since x is bigger than 2 everywhere on this interval. So r of x is a positive number divided by a positive number, right? Therefore, it's positive. So we know that the graph has to be above the x-axis everywhere from here on. Okay? Now, on this interval, well, between -3 and 2, x plus 3 is still positive. Because in order for x plus 3 to be 0 or less, x has to be -3 or less, right? And x minus 2 is less than 0. Okay? And you can kind of look at the endpoints. Okay? If x equals -3, then x plus 3 equals 0. But we don't include -3 on the interval. So all these are open intervals. And, you know, once more I'm doing things without thinking. I'm using a closed dot for an open interval. And if that confused you, good for you, because you should have been confused. Okay? I shouldn't have confused you, so not so good for me. Let me correct this and explain. falling out of my hand. Okay. It's open at this point. It's open at this point. And the purple interval is also open at this point. Okay? We're not including those points, as I said, and then I made a big old filled dot. Just gotta be careful what I'm saying, what I'm thinking. Okay, so anyhow, you got x plus, okay, again, at -3, x plus 3 would be 0. But on this interval, which doesn't include -3, x plus 3 is not going to be 0. Okay? At 2, x plus 3 is going to be 5. So x plus 2 is going to go, x plus 3 is going to go from -3 to 5. Okay? Not including -3 or 5, so it's always greater than 0. I'm sorry, x plus 3 is going to go from 0 to 5, but it's not going to include the 0 or the 5. Anyhow, that means it's positive. There are all kinds of ways you can reason out that x plus 3 is going to be positive on this interval. Convince yourself one way or the other. Just ask yourself the question. And x minus 2 is less than 0. Again, ask yourself the question. Is this greater than 0 or is this less than 0? Is this greater or less, or is this greater or less than 0? So R of x is a positive divided by a negative. Therefore, it's negative. Now, over here on this graph, we can then write positive here, because it's going to be positive on this interval. We can write negative here, because it's going to be negative in this interval. And that's a whole interval from -3 to 2. And what's happening to all my colors? I guess I'm wearing them out. Okay, and on this interval, from -3 back, both of these are negative. I don't leave myself nearly enough room, but the reasoning is pretty simple. You ask yourself the same questions. Am I dividing a positive by negative, a negative by positive, positive by positive, negative by negative, and you determine what the sign of the function is on this interval. And here it's going to be positive. So, color in the intervals. And now we know the function's going to be above the axis up to here. It's going to be below from here to here. It's going to be above from here on. That's the standard process that we follow. Now there's one more thing. We got to do the end behavior. We've got to ask if x is a huge positive number, or if x is a huge negative number, what do we get? Okay? Well, what do you think? If x is a huge positive number, what's x plus 3? Not much different than our huge positive number, right? What's x minus 2? Not much different from that huge positive number. So you're essentially dividing a huge positive number by itself. Okay? So we can reason out for huge positive x and for huge positive x. Both of these are nearly equal to x. So r of x is nearly equal to 1. And there's similar reasoning for huge negative x, which means that the value of the function, if you move far to the right or far to the left, has to approach 1. Well, here's 1. Then here's the line where y equals 1. And y, of course, is the value of the function. You can say that, okay, y equals r of x equals this, and that's what we're graphing. Okay, so can you draw that graph, and can you draw a smooth curve? Well, I guess one more thing we really have to say is, finally, if x is very close to negative 2, if x is very close to 2, what can you say about what you get when you divide this? First of all, if x is really close to 2, what's the denominator close to?
0.
Close to 0, right? So if x is really close to 2, the denominator is close to 0, numerator is close to 5, isn't it? Okay? So I can say, okay, so I'm saying x close to 2 implies that the numerator is near 5.
Okay, so class, I'm just gonna have to give up one sign. Where else?
And the denominator is near 0. Okay?
Can we not go to history or philosophy or something? Can we go to something to get some more? Where can we get some?
So y is big.
Society was saying something.
Okay? Maybe it's positive big, maybe it's negative big, but it's big.
Alex, maybe different, we were talking about science.
So I'm going to say maybe it's positive, maybe it's negative, but it's big. Okay, so see if you can sketch a graph with those characteristics.